Okay, YouTube, this is an introductory video to exponential functions in which we're really going to define what we mean by exponential growth and decay functions. So let's go ahead and start by taking a look at this function here. We have f of x equals a to the x power, where a is some non-negative number, so it's greater than 0, and we say it's also not equal to 1, and x is any number. So what you're going to see here for an exponential function is the fact that our variable is in the exponent. So we can make a little note here. Our variable is in the exponent, and that's really the key characteristic that makes this as an exponential function, is that we have this variable that's located up here in the exponent, where our base here, the base of the exponent, is really just some positive number that's not equal to 1. So this would be an example of an exponential growth function, and we could say, if we wanted to focus even further on a specific value for a, we could say, well, let's use as an example f of x equals 2 to the x power. So that being said, we want to look at the behavior of such graphs. The best thing to do is just go ahead and make ourselves a table of values. So I'm going to write a nice table of values in here. We'll put -2, -1, 0, 1, and 2. So for the sake of convenience, I'm going to start by plugging in some easier values. So start with 0. We say, what is f of 0? And of course, f of 0 would be 2 to the 0 power. What we're going to end up with is anything to the 0 power equaling 1. So I get a 1 here. How about 2 to the first power? Well, 2 to the first would be 2, and then 2 to the second power, if I put a 2 up here, would be 2 to the second is 4. You could see how if we were to continue doing this, what the pattern is that we keep multiplying our base by the value of itself because we're exponentiating it. The same thing is going backwards here. We say f of -1. I do want to confront this, but if I were to plug in 2 to the -1, remember if you have a negative exponent, what we need to do is we need to rewrite this so that its base moves over to the other side of this fraction bar, and then its exponent would become positive. So in other words, 2 to the -1 is just the reciprocal of 2 to the +1, which we get a half. And 2 to the -2, if we were to plug in a -2 here, we would say 2 to the -2 is 1 over 2 to the +2. In other words, we get the same thing as 2 squared, but the reciprocal of that. So looking at these points on a graph, I would say that this graph that you see right here is actually the graph of y equals 2 to the x. We'll look at its common characteristics, but the first one is this. It goes through the point 0, 1. And what we always want to say is that this is always the y-intercept of our graph. Our y-intercept essentially is what we get when we plug in 0 for x. And so if we're plugging in 0 for x here, we could say that anything to the 0 power is always equal to 1. So that's one key point on our exponential function graph here. We also see that at 1, we were at a height of 2, and at 2 we were at a height of 4. It doubled its height. As we were going backwards, we say at -1 here it's at a height of a half, and at -2 we're at a height of a fourth. Okay, so we get this function that as we go from left to right, since it's an exponential growth function, has a slope that is going to get even more and more increasing as we go to the right, but never gets vertical. And we could also see how the point prior to each given consecutive point is always at half the original height of the next point, or the next point is always double the height of the original point here. So key characteristics here are that we have a y-intercept here. We could see that if I had y equals 3 to the x, we still at f of 0 get something to the 0 equals 1. So this is going to be on every exponential function. The only difference here would be the height of the points off the ground depending upon the base value. So we'll take a look at this really quickly here. We notice that we have a horizontal asymptote at the x-axis. So our range is going to be all numbers bigger than 0. And the reason why we want to indicate this here is because if we would take a base value to any power, we'll never get a negative output. That's never a possibility. That is to say, if I say take 2 to the x, could we ever get a number that is smaller than 0? And I would say that this never happens. We also will never get something that comes out to be 0. As a matter of fact, 2 to the power of something must equal something, but not 0. So we would say that we have a horizontal asymptote, which is another key characteristic of this graph, on the x-axis. Okay, so we would say all exponential functions have a y-intercept at 0, 1, and a horizontal asymptote on the x-axis. Okay, so the range of this function is 0 to infinity. Its domain is -infinity to infinity. We can always plug in some x value into this function and get a y value back. It is increasing from -infinity to infinity, or at least across all of the x values. This graph is forever increasing. It is nowhere decreasing. And then our y-intercept, of course, is this important point I want to point out here, is 0, 1. So to look at this next graph here, you could say, well, what's the difference? Well, I notice that the function over here is f of x equals a to the x. Because we're plugging in now f of x equals a to the -x, this x in front, or this negative in front of the x, causes a y-axis reflection. This is just knowledge of transformations of functions here. You make your x values negative, it reflects it over the y. So you can see that we get a similar graph here, except for now we have a function that going from left to right is always decreasing from negative infinity to infinity and nowhere increasing. Important points would still include our y-intercept, which is still at 0, 1, and we have a horizontal asymptote on the x-axis. So we say y equals 0. So our range for this is still 0 up towards infinity, and our domain is still negative infinity to infinity. So what we want to know from this video is essentially that exponential functions, they're either growing or decaying from left to right, but they have this y-intercept at this 0, 1 point and a horizontal asymptote on the x-axis. We can always tell if we have a decaying graph if our coefficient of x is negative, and we'll have a growing graph or growth graph if the coefficient of x here is positive. Cheers.